So in this video, we're going to continue to talk about flux. I just want to remind you why we're talking about it first. So as you recall, we've been working with this iron bar problem, and instead of trying to break it into a certain number of stalks, we started thinking about a sort of arbitrary chunk of the iron bar in order to figure out what the partial differential equation is that describes what the temperature is moving along the bar. With that analysis, we were able to get far enough to identify that the time rate of change at a given position in the bar depends on what the flux of energy is as you move along the bar, where we defined flux as being the amount of energy that's crossing a given surface per unit time. And we also talked a little bit about the sort of idea of what flux is with regard to flux being a quantity, a physical quantity, a conserved physical quantity that crosses a given surface per unit time. So in this video, what I want to do is talk about a couple of common models for flux, and they're really the ones that you will see most often. And for each of these models, what I want to do is both talk about what it is. So what kind of flux is it? How do we actually think about it? So conceptually, what's going on? And then finally, how do we mathematically model it? Right, so those are the three questions we're going to ask. And we're going to ask those three questions about two different types of flux. The first one that we'll think about is advection. And the second type of flux that we're going to think about is diffusion. Okay. So let's start by thinking about advection. So the sort of basic idea with advection is fairly simple. Advection is flux that's due to bulk motion. And that's sort of a very fancy way of saying that if I have, let's say, a pipe, right, and there's something traveling down that pipe, water or something, right, there's actually bulk motion of the water. And so the mass that's in the water is being carried as the water moves. The energy that's in a given chunk of the water is being carried along. The number of particles is carried along. So you can think about what the flux is through some surface here. So let's say we've got some surface A here. The number of particles that pass through the surface per unit time pretty clearly depend on how fast this water is moving. So let's say this water is moving at some velocity v. So conceptually, or what kind of flux this is, it's flux that's due to bulk motion. And conceptually, you would imagine that as you make the fluid move faster, you would be carrying more stuff across this surface. Clearly, as you increase the surface area, you would get more stuff coming across it. And as you increase the density of whatever the quantity is, you would get more stuff across it. So let's do one sort of example of that, of mass flux. We could ask the question, what is the mass flux due to advection? In this case of a pipe where you've got water flowing through the pipe at velocity v. Well, if we think about that, one way to think about it is just to ask the question, how much mass is actually going to cross that this boundary, the surface A, in a time dt, right? So you're going to have this sort of hockey puck of mass that's going to pass through there, and the width of that hockey puck, right, depends on how fast the mass is flowing and also how long you wait. So this width of the hockey puck is simply going to be the speed that the fluid is moving at times the differential time that's passing, right? So the amount of differential mass that you're going to get then is simply the mass density times the velocity times dt. So the flux through the surface, right, which is simply the amount of flux mass passing through that surface per unit time, is simply going to be rho times v, and I forgot an area here, times the area, right? So the differential amount of mass is the density times the velocity times dt, which is this length, times the area. That tells me what the volume of the hockey puck is. Volume times the density tells me what the mass of the hockey puck is. So the amount of mass passing through that surface is rho times the velocity times the area. Sort of the key idea here is that the flux through that surface is proportional to what the velocity is, and is also proportional to the area, and is also proportional to whatever the density of the physical quantity is. Right? So by the same token, we could ask the question, well, how much energy is being carried across, how much thermal energy is being carried across this surface. And if we were going to do that, we'd say, well, the flux of energy being carried across the surface. Well, first, if I just look at this, it's going to be whatever the energy density is times the speed that it's crossing the surface times that cross-sectional area. And if I think about the energy density, pretty clearly that's going to depend on what the temperature is and what the mass is. So that energy density actually would be the specific heat times the temperature of the water at that particular point times the density of the water at that particular point, right? Specific heat has units of joules per kilogram per Kelvin, right? Temperature has units of Kelvin. Density has units of kilograms per meter cubed, right? Meter cubed. So kilograms cancel with Kelvin, with kilograms, kelvins cancel with Kelvin. I get joules per meter cubed, in other words, an energy density. All right, so in the same way that when I have mass flux via advection, I simply have it proportional to the mass density times the velocity. Energy flux due to advection will also be proportional to the energy density times velocity. So that's where I'll stop in this video. In the next video, we'll talk about diffusion flux.